morning friends. Today the topic of my discussion is carbohydrates. If you have followed my previous lecture, I had given an introductory discussion regarding the types of biomolecules. So in today's video tutorial, I am going to tell about carbohydrates. Now what are actually carbohydrates? As you can know from the name, it is carbohydrates. So there is a hydrate in it. Basically, carbohydrates are made up of carbon, hydrogen and oxygen. And the ratio of carbon, hydrogen and oxygen is in the ratio of 1:2:1. So from this, you can see that there is a water in it. Hence, it is known as hydrates of carbon. The general formula of carbohydrates is CnH2nOn, where N refers to the number. Okay, so carbohydrates are hydrates of carbons and the general formula is CnH2nOn. Now, depending upon the structure, carbohydrates can be classified, and this classification is strictly based on the number of units. So, let us see what is the classification of carbohydrates. When the number of units is 1, they are known as monosaccharides. Okay, you know the word mono means 1. So, you see there is another term, saccharides. The word saccharides means sweet to taste. So therefore we get another attribute of carbohydrates, that is they are compounds which are sweet to taste and they are basically hydrates of carbon, and they may be classified as follows. When there is 1 unit, they are known as monosaccharides. So what are the examples of monosaccharides? You know, the examples are glucose, fructose and galactose. However, there are many more examples, but we will tell only a few of them. When the number of units is 2, then they are known as disaccharides. Di refers to 2. Example of disaccharides are lactose, maltose and sucrose. However, there may be many such examples. Now, when the number of units is more than 2, that is when the number is 3 to 7. However, in many books you might find the number is from 3 to 10. Such carbohydrates are known as oligosaccharides. Therefore, oligosaccharides are basically carbohydrates which are made up of 3 to 7 or 3 to 10 units. So, they are referred to as the oligosaccharides. An example of oligosaccharides is raffinose. Okay. Now, next is when the number of carbohydrates, the units of carbohydrates is more than 10. That is, there are many such carbohydrate units. Such carbohydrates are known as polysaccharides. So, if you look into this classification based on the number of units, polysaccharides are the most complex form of carbohydrates, where the number of units is more than 10 and it can be many more such units. Now, some important polysaccharides are cellulose, chitin and glycogen. Okay, so based on the units, they may be of 4 types: monosaccharides, disaccharides, oligosaccharides and polysaccharides. Now, let us see what are monosaccharides. In monosaccharides, the carbon number, now we are just concentrating on monosaccharides, okay? I am giving a star here. So what are monosaccharides? As previously told, that is they are carbohydrates which have only 1 unit. In case of monosaccharides, the carbon number might vary from 3 to 7. So how are we going to get such monosaccharides? When the carbon number is 3, that compound is known as a triose sugar. So we are talking about the monosaccharides now. Okay, in monosaccharides the number of carbon, I again mentioned, ranges from 3 to 7. When the carbon number is 3, such sugar is known as a triose sugar. When the carbon number is 4, that sugar is called as a tetrose sugar. When the carbon number is 5, the sugar is known as a ribose. Ribose is an example. The sugar is known as a pentose sugar. Okay, I'm going to give the example as ribose a little later. Pentose sugar. When the carbon number is 6, it is known as a hexose sugar. And when the carbon number is 7, it is known as a heptose sugar. Now if we look into the example, so for the first one, if you recollect the steps of glycolysis where glucose is being broken down to supply energy, there is a step where glucose breaks down into two 3C compounds. They are glyceraldehyde phosphate and dihydroxyacetone phosphate. So these two, glyceraldehyde phosphate and dihydroxyacetone phosphate, are examples of triose sugars. So I am writing it as glyceraldehyde. However, there is a phosphate in it. You can also write dihydroxyacetone phosphate. Example of a tetrose sugar is erythrose. There are many more examples. We are just citing for our reference. In pentose sugar, there is a ribose sugar. Okay, ribose sugar, and there is also a deoxyribose sugar. You are very much familiar with these two sugars, as ribose and deoxyribose basically make up the structure of nucleic acids. In hexose sugar, we know the example as you can call glucose, fructose, and there are many more examples. In heptose sugar, the example is pseudoheptulose. Okay, so monosaccharides, depending upon the carbon number, may be triose, tetrose, pentose, hexose, and heptose. So in our today's discussion, we will talk in details about the hexose sugar, where we will know the structure of glucose in detail, because this is the most essential sugar, this is the most essential blood sugar, and this sugar serves as a source of energy through its breakdown. So let us see the structure of glucose. Okay, now glucose, as I have already told, is a hexose sugar, and it is basically a monosaccharide. That is, their number of carbon atoms is 6. So when we talk about monosaccharides, we are going to know a little about the isomerism of monosaccharides. In monosaccharides, there are diverse kinds of isomerisms. Today, we will talk about the functional group isomerism. When we learn about the structure of glucose, basically glucose can exist in two functional isomers. One is the aldose and another is the ketose. So it may be found in any kind of monosaccharides, but since we are talking about glucose, we are restricting ourselves to glucose. So when we learn the structure of monosaccharides, there may be two kinds of functional isomers. When a sugar has an aldehyde group, it is known as an aldose sugar, and this al refers to the aldehyde group. When a monosaccharide or a carbohydrate has a ketone group, it is called a ketose sugar. So now again we are coming back into the structure of glucose. In case of glucose, it is an aldose sugar. That is, it has an aldehyde group, and the number of carbon I again mentioned is 6. That is, glucose is a monosaccharide. The number of carbon atoms is 6. Therefore, it is a hexose sugar, and the type of functional isomer it is aldose sugar. So if we try to draw the structure of glucose, we can do it like this: 1, 2, 3, 4, 5, 6. Let us number the carbons: 1, 2, 3, 4, 5, and 6. So this makes a hexose backbone. We complete the backbone. and I've already told that this is an aldose sugar. One more important thing is that in case of aldehyde group, we have to remember that the aldehyde group is always placed at the terminal carbon. So you place the aldehyde here. So this is our aldehyde group. Now in rest of the carbons, let us see what we have. Here is a OH, here is a H, and in the third carbon the orientation of OH is in the reverse order. Next we substitute the valencies of carbon with OH and H. Okay, here is an OH, here is a H, here is a H. Now this is the complete glucose structure. Okay, and if you look into this structure, this is an open chain structure. This is an open chain structure or a straight chain structure where you find 6 carbon atoms and there are more than 1 hydroxyl groups. So such a compound where there are more than 1 OH group, such compounds are known as polyhydroxy compounds. So we get another definition or another attribute of glucose. We already know it is an aldose sugar. We already know it is a hexose sugar. And another thing is that glucose is a polyhydroxy compound. Okay, because there are more than 1 OH groups in it. So if we count the number of carbon, oxygen and hydrogen, if you count the number of carbons, you see 1, 2, 3, 4, 5, 6. So since it is a hexose, we can write it as C6. Let us count the number of hydrogen. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay. If you look into the general formula, the hydrogen should be double the number of the carbon. Now you count the number of oxygen. 1, 2, 3, 4, 5, 6. So oxygen is this. So the formula of glucose is C6H12O6. Now in case of such monosaccharides or in case of glucose, we have drawn here the open chain structure. But this glucose also exists in the ring structure. If you take an aqueous solution, you will find that the proportion of the open chain and the proportion of the ring chain conformation is equal. And one of the speciality is that the open chain can convert into the ring form and the ring form can again convert into the open form. That is, the open chain has an equilibrium or it is interconvertible to the ring form. Okay, so now we are going to learn how can we draw the ring formation of the glucose structure. It is the same structure, the empirical formula is same, but the orientation of the atoms of carbon is different. It forms a ring. Let us see how the ring is formed. In case of the ring formation, 2 carbons are important, carbon number 1 and carbon number 5. So what happens is that the elimination of water takes place from carbon number 1 and carbon number 5. Okay, so from carbon number 5 we are taking the OH group, and from carbon number 1 which has the aldehyde group we are taking H. So from here OH, from here H. So we can eliminate a molecule of water here. So if we eliminate the molecule of water, let us see what the structure becomes. 1, 2, 3, 4, 5, 6. Let us number 1, 2, 3, 4, 5, 6. Let us complete the backbone. Now let us concentrate on carbon number 1 and carbon number 5. So in between you see there is an oxygen atom. So this oxygen atom forms a bond between carbon number 1 and carbon number 5. Now you look at carbon number 6. You see 6 has its groups intact. That is, we are just satisfying the valencies of carbon. Look at the 5th carbon, here there is a H, so I have put an H here, and the rest portion, the carbon number 4, the carbon number 3 and the carbon number 2 is intact. So this portion remains intact. Now look at carbon number 1. So here all the valencies have been satisfied. Okay, let us just complete the structure. Here is OH, H, here is another OH and another H. Now in carbon number 1 you see there are two valencies vacant. So you have to satisfy the valency. So what happens is that this water which is eliminated, it breaks down into H and OH, okay? This H and OH gets added here. You put one H here and you put one OH here. So if you see the structure very carefully, it is the same structure of glucose, that is having the molecular formula of C6H12O6. But the only difference is what? There is a bond which is connected by means of an oxygen between carbon number 1 and carbon number 5. So if you want to draw the ring structure, you see there is an oxygen. There is an oxygen, okay? I'm just drawing it like this. Okay, oxygen is between carbon number 1 and carbon number 5, okay? So this is carbon number 1 and this is carbon number 5. So this is number 2, 3, 4. And if you look at the carbon number 5, there is the 6th carbon. So the 6th carbon extends as a branch. What is the 6th carbon? 6th carbon is C2OH. So this C2OH comes here. So this is basically the ring structure of glucose. Now if you very carefully look into the ring, you see the ring is basically a hexagonal ring, okay? Why hexagonal? Because there are 6 sides to it, okay? And this hexagonal ring has an oxygen. So this is a heterocyclic ring. Heterocyclic rings means that apart from carbon, there is another different atom in it, and that atom is oxygen, okay? Now if you look into the constitution, how many carbons are there? 1, 2, 3, 4 and 5. So this ring has 5 carbons and it has 1 oxygen, but it is a hexagonal ring, okay? It has 5 carbon and 1 oxygen. So this ring has a special name. It is called as a pyranose ring, okay? This ring is known as a pyranose ring, okay? This pyranose ring is the basis of ring structure of glucose, and pyranose ring is a hexagonal ring. It has 5 carbon atoms and 1 oxygen atom. Okay, now this bond which has been formed in between carbon number 1 and carbon number 5 due to the elimination of a water molecule, when it takes place within the same molecule, that is, if you take this glucose molecule, the hydrogen of the same molecule from the aldehyde group and the hydroxyl group from the same molecule of glucose, then that bond is known as an hemiacetal. So when there is a ring conformation, this bond is known as an hemiacetal bond, okay? This hemiacetal bond is referred to as a glycosidic bond when the elimination of water occurs between the aldehyde group of one molecule and the hydroxyl group of the other molecule. That is, there are 2 molecules. When this kind of an bond takes place between 2 different molecules due to the elimination of water, I am just repeating this again because it's very important. This is known as a glycosidic bond. So glycosidic bond becomes the hemiacetal bond when this elimination occurs within the same molecule. Okay, so thus from this lecture we have come to know what is glucose and what is a hemiacetal bond, and the basis of ring structure of glucose is pyranose. So in my next tutorial I am going to discuss yet another important monosaccharide, which is fructose, and we are going to compare the structural differences between glucose and fructose.